Hello, Boys State University. Thank you very much for granting me an opportunity of presenting a video. Now I am going to present a PowerPoint show on countable sets. So, what is a countable set? Many students make this mistake of trying to understand a mathematical concept by drawing an analogy with a real life situation. Now, the word countable might mean something else outside mathematics. Yes, countable means relevant. So, students might be thinking a countable set is a relevant set by uh, by some yardstick. It is relevant, okay? Or it is very easy to guess that a countable set means the elements of which are countable. That means counting of the elements of the set is over, can be finished within a reasonable amount of time. Then the set is countable. No, it's not like that. Okay, there is a definition for a countable set uh, in the mathematics, and we have to stick to it when we are inside mathematics. Now, let us see the PowerPoint show. We will define what is a countable set, then we will obtain a result on finite union of countable sets. Just give me a second. Oh, yes. So, hello, my name is Bipin Basale, and we are going to see a result on countable sets, a finite union of countable set. So, what is a countable set? A countable set is a set, it is defined as a set such that its cardinality is less than or equal to cardinality of n. Now, what is a cardinality is a very deep question. If we don't go into that, this simply means that there exists an injective function from set A into n. Okay, there exists a function f from A into n such that for any two images, if the two images are equal, then the corresponding pre-images are also equal. If f of A equal to f of A prime, then A equal to A prime, where A and A prime are any arbitrary elements of A. Now, what is this arrow symbol? Many books show this symbol, many books use this symbol for implication. Okay? But there is a certain difference between this symbol and the previously shown symbol. P single arrow Q. This is a variable statement. It is a variable conditional statement. And P with this particular implication symbol and Q. So this means tautology. That means when we are sure that if P is true, then Q is true. If we are sure that this statement is a true statement, then only we have to use this type of symbol, okay, the equal to sign followed by an arrowhead for implication. Otherwise, for a variable conditional statement, we use only this symbol. So, if there exists a function, if there exists a one-to-one function from the set into the set of natural numbers, then we say that A is countable set. Or there is alternate definition also. Earlier definition said that the existence of injective function from the set into the set of natural numbers. Now there is other way around. We talk of existence of a function from set n onto set A. Okay, now existence of surjective function. Earlier we talked of injective function from the set A into n, or alternatively, if there is a surjective function from set n into A, okay, that means for every element in the set there exists a natural number which is mapped onto this element by this function. Okay, then we say that this set A is a countable set. So these are two alternate definitions. Okay, one is one definition making use of injective function from the set A into n, and another definition which makes use of the surjective function from set n into A. Now there are very simple results that the set of natural numbers itself is a countable, because for the obvious reason that there is an identity map from the set n into set n onto n, which is injective as well as surjective. So naturally the set n is countable. Now all finite sets are countable because any finite set can be put into one-to-one and onto map on a set 1, 2, 3, 4 up to n for a suitable value of n. And if B is a countable set and if cardinality of A is less than or equal to cardinality of B, then A is countable. Naturally, if B is countable set, then cardinality of B is less than or equal to n. And since cardinality of A is less than or equal to cardinality of B, naturally cardinality of A is less than or equal to cardinality of n, because this less than or equal to relation is transitive relation, and then A is countable. And every subset, thus every subset of a countable set is also countable. Okay. Now let us come to our result. So if we are having two disjoint countable sets, then their union is also a countable set. So because A is countable, there exists injective function G from A into n. And because B is countable, there exists another injective function from B into n. Okay, which is injective function. Now it is very natural way of defining a function from A union B into n. So f of x is equal to g of x if x is in A, and f of x is equal to h of x if x is in B. Now we will try to prove that this function f is an injective function. So if f of x equal to f of x prime, then either g of x equal to g of x prime or h of x is equal to h of x prime. Really? Because here we take for granted that either x and x prime both belong to A. In that case, g of x equal to g of x prime. Or x and x prime both belong to B. Then h of x equal to h of x prime. But there is a possibility, right, that x belongs to A and x prime belong to B, and yet g of x equal to h of x prime. Okay, we overlooked that possibility and conveniently try to conclude that f is an injective function, but no, this is not correct because that possibility is always there, right? So there is always a possibility that x is in A, and x prime is in B, and yet g of x, because x is in A, it will come under G, under the mapping of, under the action of G, and g of x, because x prime is in B, it will come under the action of H, and yet h of x will be equal to h of x prime. So in this case, images are equal, although pre-images are not equal. Okay, so this kind of definition of f does not work. Okay, we discard this function, this definition, we try to define in some other way. This is that way. We define f from union of two sets into n such that f of x equal to 2 raised to gx if x is in A, and f of x is equal to 3 raised to hx if x is in B. Now this problem which occurred earlier is resolved. Okay, because even if x is in A and x prime is in B, okay, then and even if h of x is equal to, even if g of x is equal to h of x prime, still 2 raised to g of x can never be equal to 3 raised to h of x prime, right? So now that issue is resolved. So if f of x is equal to f of x prime, either 2 raised to g of x is equal to 2 raised to g of x prime, or 3 raised to h of x is equal to 3 raised to h of x prime. Okay, that third possibility is now resolved. Okay, so now it is quite easy because bases are equal. So g of x equal to g of x prime, and or h of x equal to h of x prime, and since g and h are by hypothesis they are injective functions, so we always get x equal to x prime. Thus this proves that f is an injective function. Okay, So there exists an injective function from this union into N, and this makes this union of two disjoint sets, two disjoint countable sets, a countable set. Now the same idea can be applied to any finite union of countable sets, that is, if A1, A2, AK are k mutually disjoint countable sets, then their union is also a countable set. And because each of these set is countable, there exists a corresponding function. There exists a corresponding injective function from that set into the set of natural numbers. And now we can define a function from this union into the set of natural numbers in this fashion. F of x equal to p1, p suffix 1 raised to f1 of x if x is in a1. F of x equal to p suffix 2 raised to f2 of x if x is in a2, and so on. But after all, what are these p1, p2, p3, pk? These are distinct prime numbers, and it is always possible to choose such distinct finitely many distinct prime numbers, because after all, by the result in the number theory, okay, the basic result in the number theory, the set of prime numbers is infinite. So this function is well defined, okay, no problem in defining in this type of function. And using the earlier technique, we can define that, we can prove that this function is also injective function. So thank you very much for giving me this opportunity, and please, if there are any faults with the video, please kindly intimate it to me. Thank you so much. Thank you so much for watching this video. Thank you so much.